Welcome to an introduction to AI safety, ethics, and society. In this lecture, we'll give a primer of artificial intelligence. We'll focus on different types and definitions of artificial intelligence and discuss its history. And then we'll focus on a subfield of artificial intelligence called machine learning. There are many different types of models of machine learning. Machine learning models accomplish many different tasks. They're trained on different types of data, and they output different types of data as well. And there are many different types of machine learning, such as you'll see supervised learning and unsupervised learning. Inside of machine learning is the subfield of deep learning, which we will discuss after that. And this is what most of the interesting applications of AI today currently depend on. And then we'll discuss how deep learning models can change as they are given more data, as they are given more computational resources, as they become bigger. How does their performance change? So we'll talk about all these topics. We'll focus on breadth over depth. There's a lot of content in this. The main goal of this lecture is to give familiarity with many different concepts rather than precise understanding at a highly technical level. If one is wanting a more in-depth introduction to artificial intelligence, there are many books and other resources and courses specifically for that. But this is largely just for familiarity. So let's start out talking about AI, and then we'll talk about machine learning. There isn't a universally accepted definition of artificial intelligence. It can be used to describe a branch of computer science. Somebody could say an AI is a type of machine. Somebody could say it's a tool. It's just part of a business model. Some could use AIs in philosophical thought experiments. For our purposes, we'll describe AIs as computer systems that perform tasks typically associated with intelligence, such as problem solving, decision making, forecasting, etc. That's a very broad definition, and AI has a very long history since we're using such a broad definition. So there was the Dartmouth conference, which in some ways kicked off the field. Things took longer than what some people at the Dartmouth conference expected. That AI was not something that they could solve in a few years, but that it's a very long project. Eventually, it went on for so long that there was an AI winter, which is to say that excitement in the area was substantially depressed and there was a lot less funding. Sociologically, this makes professors of AI generally on the substantially more cautious side of discussing the implications of AI or its real-world economic implications, because some figureheads hyped up AI in the symbolic AI period, and that gave rise to one of those AI winters. Eventually, there was some progress on expert systems. So instead of the AIs being hand-designed symbolically, we had experts design AIs for specific applications in their areas. And this gave additional performance by leaning on experts to provide information about what the AIs should be doing. Then there is more continued advancements in machine learning, complicated things like SVMs and decision trees and probabilistic graphical models, etc. There's a data set called ImageNet, which is a collection of around 1 million images. And that was in the prior era, but then AlexNet, which started the deep learning era, leveraged ImageNet to show that deep learning models can be very high performing. And then there were later models, such as transformers and large language models, which we'll speak about later in this lecture. There are different types of AI. There's narrow AI, which is what we had during most of the history of AI, only narrow AI systems. And these are capable of performing specific tasks only. They're not general purpose. AI systems could not do a variety of things. They could only do very specific delimited tasks. In contrast to narrow AI, there's artificial general intelligence. This is capable of performing many cognitive tasks across multiple domains at human or superhuman levels. I'll note that AGI was used in contrast to narrow AI for a long time, but now AGI is having a bit more of an amorphous definition. Some are using it as a stand-in for smarter than human intelligence. Some are using it as a stand-in for artificial intelligence that is extremely economically impactful. So the definition keeps changing. It's kind of shifting and evoking a sort of next generation or something to aspire to. But we do have fairly general purpose or multi-purpose artificial intelligence systems. And so denotatively, one could say that we have AGI by some planar definitions, but connotatively, it tends to mean a system that's much more advanced and possibly, smarter than humans in all respects. When people are mentioning AGI, it's usually unclear exactly what they're referring to other than very advanced AI systems. And then there's a more specific definition of human level AI. These are capable of doing virtually everything humans can do at a cost that's cheaper than humans, or they can do things more accurately than humans. Transformative AI are systems with a dramatic impact on the world at the level of the Industrial Revolution. So these are systems that transform the economy in very substantial ways. They're not just continuing standard GDP trends, but they are doing something quite distinct economically to the world overall in ways that show up in the productivity statistics and GDP and so on. And then there's artificial superintelligence. These are smarter than human AI systems, and they're capable at outclassing human performance on virtually all intellectual tasks. So basically smarter than any person ever. And this is usually taken to be the most advanced of these, but depending on how you define them, you could say that artificial superintelligence is just a human level AI plus a little bit of extra intelligence could be a superintelligence. But usually when people are talking about superintelligence, they're talking about something that's vastly better at doing everything humans can do and vastly more intelligent. Now let's move into the topic of machine learning. Machine learning has many different models, has many different tasks, there are many different types of data, and there's different areas of machine learning. So we'll get into all of those. So to state the relation between artificial intelligence, machine learning is a subfield in artificial intelligence. And then we'll zoom into some of the types of machine learning later. Machine learning is about developing computer systems that can learn directly from data without explicit preset instructions. So machine learning is largely about letting the data speak for itself. We will give an algorithm or a computer system a lot of data, and it will learn from that data to produce its own sorts of decisions or predictions. Machine learning systems depend on algorithms. So algorithm is a very abstract word. It's basically a procedure or recipe for accomplishing a task. So if the recipe is collect data, train on this data, and then output predictions, that would be an algorithm. That's a very abstract, vague algorithm, but that would be an algorithm. So a cookbook recipe is also an algorithm for creating some food. So algorithm can be very broad. Now, machine learning model is an algorithm designed to learn automatically from data by identifying patterns and relationships to make predictions or decisions. It's an algorithm because it will process the data and use that to make its prediction or decision. So it will follow a step of instructions, which is process the data in this way, then maybe compare it to this other data that I'm processing and check the correlation with this other thing and so on and so on. And then it ultimately makes a prediction. That is an algorithm. And that's what a machine learning model is. It's a specific algorithm for automatically learning from data to make those predictions. There are inputs. The machine learning model processes those inputs in a specific way by following a specific set of instructions, and then it produces an output. And that is what a machine learning model is at a 30,000-foot view. Machine learning models rest on or rely on training data. This is data from which the machine learning models can learn. Without that, they can't learn patterns and relationships. They can't figure out how to make decisions, so they need some data. Now, once we have a machine learning model, there's a question of access. So model developers can grant different levels of access to the public. There are closed models. These are not accessible to external use or modification. They may be used internally by organizations. So another level of access, which would be API access. API stands for Application Programming Interface. Basically, here, these are models that are accessible to the public, but you have to, for instance, you have to go online to type your queries into this system, and that could be more of an API level model. So it's not closed, but that doesn't mean necessarily that you have access to the entire model. You might just be able to give it inputs. So on the previous slide, with a closed model, you can't provide inputs to it. It's not your model. It's closed off from you. Meanwhile, an API one, you can provide inputs and you can get out the outputs, but you won't be given the internals of the model, which might be, several gigabytes or several terabytes. You won't be given that, but you will be given access to query the model or play with it. And then there's open models, and these are fully accessible and modifiable, often part of open source projects. These allows users to use, modify, and distribute them freely. You could also call these models with unrestricted access. So anybody can do anything they want with them, for good or for bad. Now, machine learning models depend on computational resources. So a buzzword in machine learning to be aware of is the word compute. Compute is basically a stand-in for the computational resources that machine learning models depend on. Machine learning models can depend on GPUs and CPUs. GPUs are a type of computer chip that are good at parallel processing, so they can do multiple things at once. Meanwhile, CPUs do things more sequentially, so this does a lot of things in a specific sequence very fast instead of doing things in parallel. There are some intrinsic design differences between the two, and depending on the type of machine learning model, using a CPU or a GPU may be more suitable. For instance, with support vector machines, those work well on CPUs. Meanwhile, deep learning models, which we'll get into later, those rely much more heavily on GPUs. The type of machine learning model can depend on the type of compute. So now let's look at the various tasks that machine learning models could be applied toward. So what's its goal? What's it trying to do? And then another question for analyzing machine learning model is what type of data does it receive? And then finally, what does it produce? So we'll zoom into the types of data. There are different types of data. There's tables, there's text, there's images, there's video, there's audio, there's time series. These are all inputs, graphs, set values, many different types of inputs to machine learning models. And those are called different types of modalities. So machine learning models that can process many different types of modalities we called multimodal. With these different types of inputs, those can be used to accomplish different types of tasks. So there are some different tasks such as classification. There's the task of regression. There's the task of anomaly detection, finding the outliers. There's other tasks like sequence modeling. So let's dive into each of those. Classification. This is about predicting categories or classes using features of an input data point. So features is sort of the parts of an input. So for an image, a feature might be a pixel. For the task of predicting whether somebody will repeat offend, a feature could be their gender or their age. So here's an example of classification. Is a review positive or negative? So given an input, a model will determine whether the input has a positive or negative sentiment. Another example of classification, is this image a cat or a dog, given an image? And so machine learning models could be trained to classify that. Another task is regression. This is about predicting numerical outputs using the input data features. So here, for instance, one could try and predict or model the relationship between precipitation and the number of umbrellas sold in some location. Another example where you could use regression is predicting housing prices given various housing features, such as the number of square feet, how many years ago was the house built, etc. And there's anomaly detection. This is about identifying outliers or abnormal data points. So given a time series input, one could identify where there are potential spikes in power consumption. In the case of images, a type of anomaly could be given a picture of a sheep. And if my model was just trained to classify whether it was a cat or a dog, it should identify the image as anomalous, that it doesn't fall into any of those two classes, that it's something unusual. Another example of anomaly detection, detecting black swans. So are there agents out there doing very unusual things, or are there abnormal trends in the economy that could pose substantial financial risks? Black swans are events that are rare and unpredictable, yet highly impactful, which we'll speak more about those in the safety engineering section. And then finally, there's sequence modeling. This is about analyzing and predicting patterns in sequential data. Generative modeling or generative AI systems do a lot of sequence modeling. These create data that resemble their input data or their training data. So ChatGPT is a generative model. It generates lots of text. It trained on lots of text and was trained to imitate it, and it outputs a lot of text as well. So it generates that text word by word. Let's now talk about the flow in creating a machine learning system. There's a pipeline of interconnected steps used in developing a machine learning model. There's the first task of data collection. Then this data may be labeled by an expert. So if you're doing classification, if you've taken many pictures of things, of say cats and dogs, you need to label whether it's a cat or a dog. Then you need to choose the machine learning model architecture. These days, this is more straightforward. People will just use transformers, as we'll speak about later, but you could choose a different type of architecture potentially. Then, given the data and given the architecture, then we need to train the model. That is where the model will look at the data and try and learn patterns and relationships in that data to make predictions. Then we have our model, and then we need to evaluate how performant it is. Is it accurate? Is it biased? Is it potentially highly hazardous? Does it have some capabilities we didn't intend for it to have, etc.? And then after we've done that, then we can deploy it. So this is a potential pipeline. Maybe while the model is training, there could be many rounds of evaluation. Maybe the model is not using labeling. So these steps can vary, but this would be a common sequence of steps. Now let's talk about evaluation. So there are many metrics for evaluation. There's the question of accuracy. Is the model accurate? What's the percentage of correct predictions? Now, accuracy can be broken down, or we might care to know more than just the accuracy, I should say. We might care to know whether there's a true positive or false positive or true negative or false negative. So using these more advanced concepts, there's some more advanced metrics such as precision. Precision is about the purity of the flagged example. So let's say we're doing anomaly detection. And let's say we're doing whether a financial record is suspicious or not, or is anomalous or not. Well, most of the financial records will actually not be highly suspicious, so it'd be easy to have high accuracy. If a model just said 100% of the time that the financial record looks good to me, is clear to go, if it said that 100% of the time, it could potentially get very high accuracy. If something like 99% of the financial records that it processes are actually okay and correct, then it would have something like 99% accuracy, even though it's saying all the time that the financial record is correct, because there's such a high frequency of financial records that are okay. So in this case, it's not flagging any of the examples, and it also has no recall. So this is not good. Although it's a very accurate model, it doesn't have good recall. So this is how we might want to break down some of these metrics and not just look at accuracy in some contexts like anomaly detection. We might care to look at precision and recall more. Here's a picture of precision and recall. But we often can just look at accuracy, but precision and recall become quite important when talking about anomaly detection, or when the events of interest are at a low proportion or at a very high proportion of the data. And when we're evaluating machine learning models, there's metrics like accuracy, precision, predictive power, and recall. But there are other things we could care about too, such as how long does it take the model to make its prediction? What's its latency? So what's the speed that the result is produced at? Is the model transparent? Do we understand the inner workings of the model that give rise to the output? Some models may be more transparent than others. Is the model highly reliable? Is it consistent in its performance under extreme stressors or in varied environments or novel conditions? Is the machine learning model highly scalable? That is, can it keep improving if we keep increasing the amount of compute that goes into the model, or the number of parameters that go into the model is constructed with, or the amount of data that the model is trained on? Or does the performance plateau? So these are other questions we may care about when analyzing machine learning models. And now let's talk about some types of machine learning. There's supervised learning, unsupervised learning, and reinforcement learning. First, with supervised learning, this is about learning from labeled data. So given images of cats and dogs, and if they're labeled as a cat or a dog, then that would be an example of labeled data. If we just had a collection of cats and dog images, but we didn't say which were cats and which were dogs, that would not be labeled. And with supervised learning, this is about learning the relationship between the input data and those output labels. So these labels are usually generated by humans. Species identification is one such example of supervised learning. This can work very well if there's a large, well-labeled data set. This isn't as suitable for highly subjective things, or it's a lot less suitable for highly subjective tasks, or if labels are extremely expensive to get, such as contract annotation. Supervised learning can be a lot less effective there because it's hard to get a very big data set for some of those very esoteric tasks. Unsupervised learning is about learning from unlabeled data. So here it's just trying to identify patterns within a data set and learning relationships between variables. So here the model could just look at text and read it, and given the text it's seen so far, predict the next word. That'd be an example of unsupervised learning. So there wasn't additional human annotation involved. Now, unsupervised learning and supervised learning are pedagogical devices. There's a spectrum of supervision, and unsupervised learning technically has some amount of supervision because we are telling the model to try and predict the next word in some contexts or in some situations. So we are providing a little bit of supervision in some sense. We're not labeling the data set, but we are nudging the model. So it's useful not to get caught up in whether it's unsupervised learning or supervised learning and acting as though there's a very hard distinction. It is more of a spectrum. For instance, you could have a fraction of your data set which is labeled and a fraction which is not labeled. And that would be a mixture. That would be semi-supervised learning. It's somewhat supervised, it's somewhat not. So it's a spectrum. Unsupervised learning is sometimes also called self-supervised learning. The model may generate signals for itself to learn from. This was kind of in reaction to people being pedantic about the word unsupervised learning because it suggests that there's no supervision going on. So self-supervised learning has gained some notoriety. And models like ChatGPT, for instance, are primarily trained with self-supervised learning or unsupervised learning. And then there's some additional supervised learning that comes later in the process. But the vast majority of their representations come from unsupervised or self-supervised learning. We'll look at an example of self-supervised learning in vision. So here's in painting. Basically, delete random parts of the image, and the model has to fill in the blank and recover what should be there. And then we can estimate how accurate was what it infilled. Did it infill what was originally there before those pixels were deleted? So that can teach these vision models about what images look like and the relations between various pixels. So unsupervised learning can be for text and images and many other different types of inputs or modalities. And then a third type of machine learning is reinforcement learning. And this is learning from agent-gathered data. So AI agents perform a sequence of decisions, and they try to improve their performance based on responses to their environment. So if a robot is navigating through an environment, it may try and do so with trial and error. So it may be going through an obstacle course of some sort. It's learning through trial and error, and it's getting steadily better and better. And then when it reaches the goal, then it gets a positive reward. Reinforcement learning is largely used to describe what goes on for AI agents or a set of methods for AI agents, but this is starting to become less the case. We're starting to see that AI systems produced through unsupervised learning can be repurposed to be agents, and so reinforcement learning may not be necessary for getting AI agents. So here's some different flows of the training data. Supervised learning has training labels, whereas unsupervised learning does not have training labels. They both have loss functions. In reinforcement learning, there's instead rewards, like it accomplished the goal or not. It drove the person home safely or not would be an example reward. A very high level comparison. There is not fixed data. The environment instead is what the agent is directly learning from instead of a more static training data source, as is more often the case in supervised learning and unsupervised learning. So to recap, AIs are computer systems that perform tasks typically associated with intelligence, such as problem solving, decision making, forecasting, etc., and they can be classified according to their capabilities. Machine learning is a subset of AI, and these learn directly from data without following explicit preset instructions. They can do things like classify things, they can do regression, they can do anomaly detection, they can do sequence modeling. Machine learning requires data, it requires an architectural choice, which needs to be trained and evaluated before it's deployed. Machine learning models can be supervised. They could use unsupervised learning. They could use reinforcement learning. They could use a mixture of all three of them. But right now, the thing doing most of the heavy lifting is unsupervised learning. And then on top of that, there's a bit of supervised learning. And then there's a small amount or no reinforcement learning on top of that. Unsupervised learning is providing the bulk of the quality of the representations of existing cutting-edge machine learning models, namely deep learning models, which is what we'll get into next. We'll talk about deep learning, and then we'll talk about how deep learning models scale as the resources put into them vary. So let's look at deep learning. Deep learning is a subfield in machine learning, which is a subfield of artificial intelligence. So deep learning uses neural networks. These are layers of interconnected nodes that transform inputs into outputs, and these are inspired by biological neurons. So these are in some ways a coarse approximation or simulation of many of the processes in the brain. Now, there are many inaccuracies. They don't fully simulate what goes on in brains in much the same way that airplanes do not fully simulate birds flapping their wings, nor do they have feathers, but they do get some of the key features right. Deep learning models extract useful patterns from large quantities of data. So they scale very well with respect to data. As data increases, they don't plateau very quickly. They can keep improving. And they learn hierarchical representations of the world. Deep learning uses many layers of neurons. And since there are many layers, this allows them to learn more hierarchical compositional representations. Again, this is 30,000-foot view, so quite abstract words. So in contrast, there's a hand-designed program which produces an output like check if their income is less than this and if they are this old and checking for some of the specific things. This would be a hand-designed rule-based program. And that is an older type of system. In contrast to that, there are machine learning models which don't have their logic solely proceed by manual construction. Instead, they just learn from a lot of data, learn from a lot of features in data, and then that lets them produce the output. But deep learning models primarily just take in the raw input and can output various decisions or other interesting types of data. They can take in images and output images. Meanwhile, all different types of machine learning systems have difficulty taking in images and outputting images in a useful way. Or deep learning systems can take in text, such as a description of an image, and then the deep learning system can output an image corresponding to that input text, whereas other machine learning models are not very capable of doing that sort of thing. So the hand design element has been eroded with deep learning systems, and they will automatically learn much of the stuff. So there's a lot less human involvement for these deep learning systems. That is to say that how they process things is not as hand designed as it used to be. It's not like typical software where every decision or sub-decision it makes was manually crafted. That's not the case for deep learning systems. They will automatically learn how they want to process data. So deep learning matters because it's extremely performant. In some domains, it's superhuman. It works across a variety of modalities, images, chessboards, Go boards, text, etc. There's a lot of real world utility. It can be used for healthcare. It can be used for recommender systems and social media. It can be used to process LiDAR data or visual data in autonomous vehicles. The deep learning models are highly scalable, so they don't plateau very quickly, whereas machine learning models might taper off or saturate in their performance. So these features have made deep learning quite impactful. Deep learning model performance is affected by algorithms, data, and compute. This is sort of the holy trinity of deep learning, so to speak. The algorithms would be things like the architecture. The data would be the data set that it trains on. Is it a very big blob of data, or is it just a few thousand examples? This makes a substantial difference. And how much compute, how many GPUs did it train on is also a very relevant factor. So if one's wanting to influence what deep learning models do, one would want to influence their compute, their data, or the algorithm that processes the data and exploits the compute. Now let's talk about some of these algorithms and these building blocks of machine learning models. There's this thing called multi-layer perceptrons, and then we'll talk about activation functions, and then residual connections, convolutions, and self-attention. So these are very technical concepts. I am presenting them mostly for familiarity. There's a lot of technical words, but there's just to have some exposure to it. So if you forget half of it, that's fine. It's just useful to confront these concepts at least once. Let's speak about the first building block, multi-layer perceptrons. MLPs are a foundational neural network architectural building block. These MLPs have multiple layers of neurons. There are input layers, there are hidden layers, and there's an output layer. We can see that each circle is representing a different neuron, and we can see many neurons are connected to neurons at the next layer. And this data is processed in a sequence, which specifies an algorithm, and these come together to result in the predictions in the output layer. So the information flows in one direction, so it's said to be fed forward. So it's a feed-forward neural network. Now let's talk about activation functions. These are nonlinear functions applied to the weighted sum of each neuron within a layer of a neural network. So the activation function transforms the weighted input sum into an output signal, which is then fed to the neurons at the next layer. If we look at this specific neuron here, it's receiving inputs from the previous layer, and it will output to the next layer. The different connections may have different strengths or weights. So that neuron that we're looking at has a strong connection to the first neuron of the previous layer, and a somewhat strong connection to the third neuron in the previous layer, but the other two neurons don't have a very strong connection. There's a simple added bias. This is a technical term. It takes the inputs of these previous neurons, and then also maybe a constant is added. These are all summed up, and then an activation function is applied to that weighted sum plus that bias. And then that produces a single value. And then that information is fed to the next neurons, the next layer. So what are the functions applied to that weighted input sum? Well, there are a few key activation functions. There's the ReLU, there's the GeLU, made by yours truly, / the CeLU is a variant of that, made by yours truly. And there's the sigmoid and the multidimensional version, the sigmoid, the softmax. So we'll just look at ReLUs, GeLUs, and sigmoids. So the ReLU looks like that. If the input is negative, it just makes it 0. If the input is positive, it lets it through. So gate it based on its sign. If it's negative, don't let it through. If it's positive, let it through. Why might this be relevant? Well, let's say we have some whisker checking neuron. If it sees something that's negatively related to whiskers, it's unclear what that could be. Planes are unrelated to whiskers, chairs are unrelated to whiskers, et cetera, et cetera. But if we see something positively related to a whisker, now we actually know what this is. So there may be some asymmetry between that sort of negative knowledge and positive knowledge. The GeLU is different. Instead of gating by the sign, instead we're going to weight it by its input size. So if it's very positive, you let it through completely. If it's somewhat negative, the smaller it is, the more I will dampen whether it goes through. So instead of a hard gate by sign, it's sort of a gating by the size of it. And the sigmoid has an output between 0 and 1. So this could be thought like a firing rate probability. So the larger the input, the higher the probability of firing, but instead of firing, it's instead some smooth thing. So instead of being a step function of if it's positive, let it through. If it's negative, don't let it through. Or if it's positive B1, if it's negative B0, instead this is a smooth approximation to that. So these are obviously very alien, and I gave some intuition just a moment ago of, what the ReLU might be doing, for instance, but truth be told, there is no canonical explanation for why these activation functions work as they do, or why they have been useful building blocks inside of neural networks. It's basically like people who, claim to have extremely strong intuitions are fooling themselves. One example is the sigmoid would claim. Sigmoids were very popular in neural networks, and they fell out of favor, and they were replaced with ReLUs and then eventually GeLUs. But there's the multidimensional version of the sigmoid. The softmax is now used in neural networks again a lot. So there are a lot of stories about, why the ReLU is so superior to the sigmoid, many conceptual arguments, but those weren't true because we are using basically things like sigmoids, softmaxes again, and we're doing so just fine. They're being very performant. So with most of these deep learning building blocks, there really is not actually a solid intuition. There can be some advanced technical intuitions that would suggest to a researcher to invent it. So I had some technical intuitions that led me to guess the GeLU activation. But what ultimately decided whether it would be used or not was whether it improved performance. So the answer to why do we use these is because we threw a lot of stuff at the wall and saw what stuck. It was a very large space of guesses. Some of us made better, more complicated guesses, and then they were empirically validated and the performance was measured. And if they reliably improved performance, then they were adopted. So that's the primary explanation for why are these functions that stood the test of time. And it's because of their performance. Other intuitive arguments should be treated in a specious way. And likewise for other building blocks in neural networks, such as residual connections. Residual connections are pathways for information to bypass network layers. So data can skip being transformed in each layer, and the original content can be better preserved. So at the left is a normal feed-forward layer. At the right is a neural network with residual connections. Each layer can access more than just the previous layer's representations. Lower level features from earlier layers contribute directly to higher level features of deeper layers. So by facilitating the information flow, they help models learn iterative and hierarchical feature representations. So you can see here's a lot of vague words, and it's kind of right, but is this why residual connections are so popular? Because they perform really well. Many different interpretations of what's going on. You could say it helps with optimization. You could say it helps the training process go more smoothly. But, it's some evidence to suggest that another intuition, it's like a read and write layer. So there's a read path that each layer will read from, and then it will modify, and here's the editing thing. So this function will come with an edit to the information stream or the residual stream. So it will apply an edit, and it will go through this and apply an edit, but the mainline content is the same. And these functions will just learn to edit. Instead of edit and carry this stuff forward, we've separated the two functions. This is an intuition. I think this intuition has some mileage, but there could be many other types of things. You could say, oh, it makes some other technical stuff like the loss surface smoother and so on and so on. So the main bit to take away is, why do we have these weird alien things? We tried lots of stuff. There were lots of things to try. Some made much more plausible guesses than others. And then a small subset of those worked particularly well and stood the test of time. So very much an evolutionary artifact that was determined by experimentation as to whether the building block would survive or not big intellectual insight. Convolution is another building block. This is a process used to detect patterns in the data by applying a small matrix called a filter or kernel and looking for cross correlations. Okay, so there's a lot of technical mumbo jumbo. I'm mentioning these building blocks for some familiarity. This jargon is not something you need in thinking about AI risk in particular, but it's useful to come across it at least once, as I've said before. So here's an example filter. Here's some example data. This filter maybe could be checking for an edge, and the data is lots of pixels. So this will sort of slide across, sort of looking for whether a pattern is similar to what the filter is. And these will result in different sums. And if there's something that looks more like an edge, then the activation map will be higher in the region that looked more like an edge. So that's convolution. This is primarily used in vision models. And now let's talk about one of the key building blocks, or one of the most recent building blocks from 2017, which would be self-attention. Self-attention encodes relationships between elements in a sequence. Each element attends to every other element by determining relative performance and focusing on the most relevant connections, capturing relationships within sequences that are separated by long distances. Here's an example for summarizing text. The model is attending to some certain words more than others, so it's learning to attend to some different words. But the self-attention is a building block in the transformer. The transformer is a deep learning architecture used in LLMs and other models. Transformers consist of transformer blocks, which combine self-attention and MLPs and residual connections. The MLPs use usually the GELU or activation function. So it puts all these sorts of things together. Self-attention affects a residual connection. There's some specific thing called layer normalization, which you can just forget about. Those are processed by MLPs. The MLPs are an internal neural network, which use often a GELU activation function, which affects the residual connection, and so on and so on. So that whole thing is a transformer block. And when you stack many of them, that's a transformer. I think this should look fairly alien. There's not that much rhyme or reason. Largely people, swapped around the order of these sorts of things, glued them together in many different ways, and then found that some combinations were much more performant than others. An example transformer would be LLMs, or large language models, which these days rely on transformers. They could use different architectures too, but they primarily use transformers. Those LLMs have many different parameters. So they have many transformer blocks. They have MLPs with many different neurons. They train on vast quantities of training data, and they use self-attention and other sorts of things to model connections between different inputs or different parts of the input. Okay, so we've now discussed the different building blocks. Then there's how to create the architecture. There's a question of how are these trained? What's going on in training at a high level? Well, the neurons are usually randomly initialized when training begins, and then they start to learn and decrease their loss. So the models are initialized. Input data is fed forward. So this could be like a sequence of words. And then there could be loss, like given the sequence of words, what word will come next? And that can constitute the loss. And whether it got the answer right or wrong would affect its loss. And that would tell the model how it should update in this thing called backpropagation. That's where you adjust the parameters of the weights of the network so that it's better at making predictions and has a lower loss. So in this figure, there's this loss surface, and these theta things are different parameter values. And the goal is basically to adjust the parameters so that the loss decreases. And if you initialize in different locations, the model may have different losses. Deep learning models are, fortunately these days, not that sensitive to parameter initialization. So basically, the model is initialized, there's forward propagation, loss calculation, back propagation, the weights are updated. Then we take a new data point, feed that forward, have the model make its prediction, calculate the loss, back prop by finding out what we should update the parameters to, and then actually update them, and then repeat. So you loop through 2 through 5 continually until it's time to stop, until the loss is sufficiently lower, until we've looked at the data for enough time. And that is an algorithm, a training algorithm, or a training recipe. So a model's parameters are set to some initial values, often small random numbers. These values define a starting point for the training of the model and can have significant influence in its success. In the context of deep learning, tends not to matter as much. If we initialize not randomly, but from a model that has trained on a different task, that can definitely increase its ability to accomplish a task. Forward propagation. The input data is passed through the model layer by layer. Neurons in each layer perform their specific operations via weights, biases, and activation functions. Once the final layer is reached, an output is produced, and we may be feeding forward many examples simultaneously, and those are called batches. There's a loss function, which quantifies the difference between the prediction of what it should have been and what it actually was. The loss represents the error. And there's this thing called backpropagation. The error is propagated back through the model, starting from the output layer. It goes backward all the way to the first hidden layer. And this is used to compute, technical words, gradients and things like that. This is used to calculate the way in which the parameters should update. So given the update signal, there's an optimizer which says how much to update in that direction. And there are many different types of optimizers, such as gradient descent. Atom is also another optimizer, stochastic gradient descent. There's gradient descent with momentum. There's lots of optimizers. And then steps in 2 through 5 are repeated many times until the loss decreases enough, or until we run out of data or run out of time or run out of compute. It may look at the data set multiple times. When it's looked through the entire data set once, that could be called an epoch. So there's a lot of technical words, but high level, this is a training algorithm for teaching a neural network. And there's some complicated steps involved with optimizers and loss functions and gradients and batches and so on. But this is a look under the hood. You don't have to understand everything that happens, but we'll pass this point by. There are some different types of training methods, and the details here are more worth remembering. There's this concept called pre-training. This is where we train a model on vast quantities of data to give it many generally useful representations. And these representations are encoded or stored in the model's weight. So if we train a model to write a movie script, it would make sense to pre-train it so that it just learns how to speak in the first place. So have it doing basic language modeling is fairly useful if you want to write a movie script. Another training method is fine-tuning. Given a pre-trained model, we customize it for some specific task using some additional data. We initialize the model using the pre-trained model weights. And this can give it a lot more representations, a lot more quality representations compared to if we use a randomly initialized model. So if we use the pre-trained model weights instead of random weights, then if we use this fine-tuning data, then we'll be much more successful. Then we will customize some or all of the layers of the network. We'll adjust the weights of them so that it's better at accomplishing a specific task. Maybe it's trained to predict the score that reviewers will give a movie script. And there might be a specific small data set, and we might leverage a pre-trained large language model that knows how to read and write for the pre-trained weights. Another training method is few-shot learning. This is using a much smaller amount of data. This is most effective after a model has a very strong representation. So you basically need a pre-trained model for this. And here the models are just given a few examples to quickly discern the pattern and figure out the correct answer. So in few-shot learning, you could give it a few restaurant reviews and teach it to say that this restaurant review is positive, this restaurant review is negative. You give it a few of those examples, and then it's basically supposed to figure it out. So figure out, given a new restaurant review, whether the review was positive or negative. And now for the final section on scaling laws. This is analyzing how precisely do models improve with scale. So scaling laws for large language models or for neural networks predictably model how AI systems' performance scale with resources, or some aspects of their performance scale with resources. The crucial inputs to a scaling law are the parameter count and the dataset size, both of which are bottlenecked or depend on compute. The scaling laws detail the relationship between AI model performance and its primary inputs, namely parameter count and dataset size. Before looking at those equations, we need to learn a little bit more about these sorts of equations in the first place. So scaling laws are a type of power law. So y equals b to the xa is a power law. So y equals x squared is therefore a power law. Y equals x to the negative 2 is also a power law. The change in y is proportional to a change in x raised to the a. And if we take the log of both sides, we can see that we have a variable, or we have a quantity, log x equals a times log y plus another constant. This power law relationship is linear in this logarithmic space. X and y can vary together in a more linear way if we take the logs of both, which we'll see in a moment. But these power laws are very ubiquitous. They're not just specific to deep networks. They're found throughout nature and society. Earthquake magnitudes, social media content generation, wealth, city populations, etc., have associated power laws. Here's a power law, and if we took a log on both axes, then it would end up behaving linearly, and that's what will make it a power law. So these occur elsewhere. And in deep learning, as mentioned before, the loss has been on parameter count, aka model size, and the dataset size. So scaling laws let us predict the overall loss. This would be the loss of the ability to predict the next word. This isn't telling us the performance on very specific tasks. It is telling us this overall language modeling ability. Scaling laws do not mean we can reliably predict what the next future capabilities will be, but they allow us to at least predict overall what's the loss going to be for a model trained with this many parameters and trained on this much data. What would the language model loss be? But it won't tell you if, the AI will suddenly become sentient, or it won't tell you now the AI knows how to make a bioweapon. That is not what scaling laws will tell us. So it adds some predictability, but it doesn't let us predict a lot of the more specific capabilities. The model size is measured in parameters. Those parameters are the model's adjustable weights. The data size is measured in tokens, which are basically like words. They might be subwords, such as walk and ing might be two different tokens. So it might split up the words a bit into subcomponents, and those subcomponents can be called tokens. But anyway, loss falls non-linearly or follows a power law as the number of parameters and tokens increases, and therefore the performance of the model is highly dependent on the amount of compute that goes into them and the amount of data and the amount of parameters. So compute lets there be more operations be done. That means there can be more parameters and also means that more data can be processed. Here's an example scaling law from a large language model made by DeepMind called Chinchilla. It basically had this formula. So there was this N, it was the number of parameters, D was the number of tokens, and it was basically saying the loss is this function of the number of parameters, the number of tokens. So if you say, I will train on this many parameters, I will train on this many tokens, this is what my loss will be. And so if you plot it, here are different models. Here's the loss, and there's flops, which is a function of compute. As compute increases, we can increase the number of parameters and number of tokens, and this allows us to get a lower and lower loss. These charts are very interesting to read. This yellow curve, this means the first batch, the first set of examples that are processed, used up more compute being measured in flops, used up more compute than the entire training run of this 75 million parameter model. This is 10 billion parameter model, which was using more and more compute as training went on, even at the very beginning, used up more compute than the smallest model throughout its entire training run. And we can see that these scaling laws hold for many orders of magnitude. That's a very robust phenomena. So if somebody's saying that, oh, the loss will not continue decreasing as we continue to scale it, this becomes a harder and harder thing to assert as the scaling laws continue working. So let's discuss these scaling laws. We can see that these scaling laws hold across many orders of magnitude, that is factor of tens. They hold across different modalities, such as text and images and video and audio. They apply to both small and large models. The scaling laws describe some machine learning models more closely than others. So generative models like LLMs follow the scaling laws, but more complicated ones or older ones like discriminative models, that is things like classifiers for cats versus dogs and things like that, don't necessarily follow scaling laws. They certainly benefit from more parameters and more training data, but they don't necessarily follow this functional form. But that said, most of people's interests these days are on generative models. And scaling laws are not necessarily fixed, they can change. So there can be better learning algorithms that have different parameters. So you could imagine creating a new machine learning system that has a different coefficient here and a different exponent. But largely, algorithmic development improves these sorts of constants and tends to do less in improving the exponents across more and more orders of magnitude. And now let's talk about an implication of scaling laws, which would be the bitter lesson. We've seen in the past that AI researchers have tried to improve systems using expert knowledge. They're expert systems. They're hand-designed features that people created. They tried injecting their knowledge to improve the AI systems. But the bitter lesson says that this leads to improvements in the short term, but it can even hurt long-term development. Instead, what you want to do is find methods that scale better, things that better leverage computation and data. Don't try and inject your specific fragile knowledge. Let the data speak for itself. Find methods that just better leverage that compute. So while people want to use their advanced knowledge of some specific area, these just tend to be displaced with algorithms that are better able at leveraging compute and data and are not baking in assumptions or using expert knowledge. So the bitter lesson is that simple methods that can really leverage scale in compute and data and things like that are better than complex research approaches, ones that use, very fancy mathematics or use complicated domain-specific knowledge. These tend to get beaten by these fairly dumb methods like deep learning methods. So this is not fun for researchers because it leaves them less to do. There's less ways they can use their knowledge to make the systems better. Actually, they scale pretty well, and it's pretty hard to improve on the building blocks. And so actually, much of the game of making better AI systems, most of the game is acquiring more resources so you can buy more compute, you can buy more GPUs, and so you can harvest more data. So to recap, deep learning is a set of techniques used to create highly capable ML models, such as neural networks that have many layers. And deep learning models as building blocks include these neural networks such as MLPs, activation functions, residual connections, convolution, and self-attention. Self-attention, residual connections, activation functions such as the GELU and MLPs all can come together to create a transformer block, and transformers consist of transformer blocks. And scaling laws describe how performance increases when parameter count and dataset size increase. And scaling laws hold across many modalities and across many orders of magnitude. The bitter lesson identifies that performance mostly scales with these inputs rather than with specialized knowledge. The specialized expert knowledge does not do much heavy lifting compared to bigger data sets and bigger computers.